I'm Robert Bruce Thompson, and this is the Home Scientist video series. In this segment, we'll react the copper 2 carbonate that Dr. Mary Chervenak made in segment 4 from root killer and baking soda with distilled white vinegar to make copper 2 acetate, and with the pure hydrochloric acid we made in segment 7 to make copper 2 chloride. I purified Mary's copper 2 carbonate by washing it several times in 500 milliliters of tap water, letting it settle each time, and then decanting off excess water. This procedure, including a final wash in distilled water, removed essentially all of the sodium sulfate and other soluble contaminants, leaving only very pure copper 2 carbonate. Incidentally, I misspoke in the first video when I said that Mary had produced 100 grams of copper 2 carbonate. She started with 100.35 grams of copper 2 sulfate, which is about 0.4 moles. Each mole of copper 2 sulfate yields 1 mole of copper 2 carbonate. The formula weight of copper 2 carbonate is 123.55 grams per mole, so the theoretical yield was actually only about 49.4 grams. After washing, drying, and weighing the copper 2 carbonate, I found that I had about 47 grams of product, about 95% of the theoretical yield. Since copper 2 carbonate is extremely insoluble, nearly all of the shortage was mechanical loss. Crystals stuck to the beaker or filter paper and so on. Let's get started. The first step in any synthesis like this is to balance the equations and run the stoichiometry numbers. I started with about 0.4 mole of copper 2 carbonate. I decided to convert about 0.1 moles to copper 2 acetate and 0.2 moles to copper 2 chloride. The formula weight of copper 2 carbonate is 123.555 grams per mole, so I've weighed out 12.36 grams of copper 2 carbonate for conversion to the acetate, and 24.72 grams for conversion to the chloride. 1 mole of copper 2 carbonate reacts with 2 moles of acetic acid to form 1 mole of copper 2 acetate, so I'll need 0.2 moles of acetic acid. Distilled white vinegar is 5% acetic acid, or about 0.87 molar, so I'll need about 230 milliliters to provide 0.2 moles of acetic acid. I'll use 250 milliliters of the distilled white vinegar to make sure the acid is in slight excess so all of the copper 2 carbonate reacts. Although it's not strictly necessary, I also want to have enough water present to completely dissolve the expected yield of copper 2 carbonate. That way I can filter the solution to remove any undissolved solids without losing product. The formula weight of anhydrous copper 2 acetate is 181.635 grams per mole, so we expect to yield just over 18 grams. At room temperature, the solubility of copper 2 acetate is about 9 grams per 100 milliliters, so the expected yield should be completely dissolved by the 250 milliliters or so of water present in the reaction vessel. Doing similar calculations for the chloride, we see that 1 mole of copper 2 carbonate reacts with 2 moles of hydrochloric acid to form copper 2 chloride. So for my 0.2 moles of copper 2 carbonate, I'll need 0.4 moles of hydrochloric acid. The formula weight of anhydrous copper 2 chloride is 134.45 grams per mole, so our expected yield of 0.2 moles is 26.89 grams. At room temperature, the solubility of copper 2 chloride is about 73 grams per 100 milliliters, so our 26.89 gram expected yield would completely dissolve in only about 37 milliliters of water. But 0.4 moles of hydrochloric acid in 37 milliliters of water is about 10.8 molar. That's pretty concentrated and reacts very vigorously, so I decided to dilute the acid significantly. That'll give me more water to boil off, but that's a minor problem. Okay, with the calculations complete, let's do the actual reactions. As you may remember, the wet copper 2 carbonate that Mary made was distinctly blue, but you may be able to see our dry copper 2 carbonate is a nice green color that's typical of anhydrous copper 2 salts. In dry form, the green color of unsolvated copper 2 ions predominates. In hydrated salts or in aqueous solutions, copper 2 ions form complexes with water as a ligand. Those complexes are blue. To begin, I'll transfer the 2 portions of copper 2 carbonate to our reaction vessels. And I'm going to do a quantitative transfer here by rinsing any remaining copper 2 carbonate down and into the reaction vessel. Doesn't hurt to have some water wetting it down to slow down the reaction with the acid. So I'll gradually add the acids to the reaction vessels, and I'll begin by adding a small amount of the acetic acid of the vinegar to see how vigorous the reaction is. And as you can see, we get some bubbling, but it's not reacting with extreme vigor. So I'll swirl this a bit and try adding a little bit of the hydrochloric acid to the other vessel, which is considerably more vigorous. You may be able to hear the outgassing of the carbon dioxide. And as you can see, the reaction is about complete. There's still a minor amount of foaming, outgassing, but most of the copper carbonate has reacted with the hydrochloric acid to form beautiful Kelly green copper 2 chloride. Meanwhile, our copper carbonate is reacting very slowly with the acetic acid. It will continue to outgas gradually as the reaction continues. So we'll just allow it to sit until it's dissolved fully. Okay, we've allowed the copper 2 acetate vessel to react for a few more minutes. You may be able to see on the video there are still bubbles gradually arising and popping at the surface as the acetic acid reacts with the copper 2 carbonate. Other than just the bubbling, one way we can tell the reaction is taking place is the change in color. Rather than the original pale green color of the copper 2 carbonate solid and initially as the suspension when we stirred it into solution, you can see that the solution is assuming a much more distinctly blue coloration that's characteristic of copper 2 acetate. So we'll allow that solution to sit for a while longer, possibly overnight, to finish the reaction, and we'll then have pure solutions of copper 2 acetate and copper 2 chloride. Okay. At this point, we have solutions of relatively pure copper 2 acetate and chloride. How you proceed from here is up to you. For many purposes, no further purification is needed. We used pretty pure reactants, including the food-grade vinegar, so the products are also pure, probably lab-grade or better. You can use the solutions as bench solutions. There aren't any mechanical or other losses, so you can just calculate the theoretical yield of each product and the resulting molarity of the solutions and label the bottles accordingly. If you need solid product, evaporate each solution to dryness under gentle heat to yield the acetate monohydrate and the chloride dihydrate and transfer them to labeled bottles. If you need purer product, you'll need to recrystallize the salts. Unfortunately, the solubility curves for both salts are poor for recrystallization. Only about 3 times as much copper 2 acetate dissolves in a given amount of boiling water as in nearly freezing water, and less than twice as much copper 2 chloride. In other words, with simple recrystallization, you can expect a yield of purified product of only about 2/3 the mass of copper 2 acetate you start with, and with copper 2 chloride less than half. That's a lot of product to waste in recrystallization losses. In the next segment, we'll use a procedure called serial, progressive, or iterative recrystallization, a technique that maximizes yield while maintaining very high purity. Please subscribe, rate, and comment.